Imagine a telescope so far from Earth that a signal takes 16 minutes to travel between it and our planet, yet it's already peering back 13.5 billion years, capturing light from galaxies born in the universe's infancy. This is the James Webb Space Telescope, a 6.5-meter marvel of engineering suspended in the cold void of space, its gold-plated mirror slicing through cosmic dust to reveal secrets our eyes could never see. Launched in 2021, it's not just the largest ever built, it's a time machine, stitching together the story of stars, planets, and the origins of life itself. But how did it get there? And why does it look like a flower made of mirrors? Let's unravel the science behind the most revolutionary telescope in human history. The James Webb Space Telescope has transformed our understanding of the cosmos by unveiling ancient galaxies and distant worlds that were previously hidden from view. At the heart of this breakthrough is its ability to peer into the early universe, capturing light from galaxies formed just 200 million years after the Big Bang. These revelations are not just about seeing farther, they're about rewriting the story of how the universe evolved, how stars and planets formed, and even what might lie beyond our solar system. But how did this telescope achieve such extraordinary results, and what exactly has it shown us so far? Let's explore the science behind these discoveries and the profound questions they raise. The James Webb Space Telescope is the most advanced observatory ever launched into space, designed to build on the legacy of the Hubble Space Telescope while pushing the boundaries of what we can observe. Unlike Hubble, which primarily captures visible light, Webb is optimized for infrared wavelengths. This is critical because the universe is expanding, and the light from distant objects has been stretched over time into longer, redder wavelengths. By detecting infrared light, Webb can see through cosmic dust clouds and observe the faint glow of the earliest galaxies, which are too distant and ancient to be visible in visible light alone. Its mirror, 6.5 meters in diameter, more than twice the size of Hubble's, collects more light, allowing it to detect even the faintest signals from the farthest reaches of space. But its true power lies in its location. Webb is stationed at the second Lagrange point, a stable position about 1.5 million kilometers from Earth, where it can operate without interference from Earth's atmosphere or sunlight. This remote vantage point ensures it can capture data with unprecedented clarity and sensitivity. One of the most groundbreaking discoveries made by Webb is the observation of galaxies that formed just 200 million years after the Big Bang. These galaxies, some of the oldest ever detected, are incredibly faint and distant, their light taking billions of years to reach us. By analyzing their light, scientists have gained insights into the early universe's structure and the processes that led to the formation of the first stars and galaxies. For example, Webb has revealed galaxies that are not only ancient but also massive, challenging existing theories about how galaxies grew so quickly in the universe's infancy. These findings suggest that the universe may have had more complex structures and interactions in its earliest days than previously thought. Additionally, Webb's infrared vision has allowed researchers to study the chemical composition of these ancient galaxies, identifying elements like oxygen and carbon, key ingredients for life, as they formed. This provides a window into the cosmic recipe that led to the creation of stars, planets, and ultimately, life itself. Beyond galaxies, Webb has also shed light on the birthplaces of stars and planets. In the dusty nurseries of star-forming regions, Webb's instruments have captured detailed images of protoplanetary disks, clouds of gas and dust where new stars and planetary systems are born. These disks, which can span millions of kilometers, are the cradles of planetary formation, and Webb's high-resolution imaging has revealed intricate structures within them. For instance, scientists have observed gaps and rings in these disks, which may indicate the presence of young planets orbiting the central star. By studying these features, researchers can better understand the dynamics of planet formation and how planetary systems evolve over time. Moreover, Webb's ability to detect the faint glow of newly formed stars has allowed astronomers to map the distribution of star-forming regions across the universe, providing clues about how star formation rates have changed over cosmic history. These insights are crucial for understanding the life cycles of stars and their role in shaping galaxies. Another major breakthrough from Webb is its ability to analyze the atmospheres of exoplanets, planets orbiting stars outside our solar system. By observing how starlight passes through a planet's atmosphere, scientists can detect the presence of specific gases, such as water vapor, methane, and carbon dioxide. These atmospheric signatures offer clues about the conditions on these distant worlds and their potential habitability. For example, Webb has already identified water vapor in the atmosphere of a gas giant exoplanet, a discovery that highlights the telescope's capability to study the chemical makeup of alien worlds. While these planets are unlikely to be habitable as we know it, the data collected by Webb is paving the way for future missions that could search for signs of life beyond Earth. Additionally, Webb's observations have revealed unexpected phenomena, such as the presence of heavy elements in the atmospheres of young exoplanets, which suggests that planetary systems may form and evolve in ways that were previously unimagined. The significance of these discoveries extends beyond the technical achievements of the telescope itself. They are reshaping our understanding of the universe's origins, the processes that govern star and planet formation, and the potential for life beyond Earth. For example, the detection of ancient galaxies has forced scientists to reconsider the timeline of cosmic evolution, while the study of exoplanet atmospheres is opening new avenues for astrobiology. These findings also underscore the importance of long-term, large-scale scientific endeavors like the James Webb Space Telescope. Unlike ground-based telescopes, which are limited by atmospheric interference, or even the Hubble Space Telescope, which operates in low Earth orbit, Webb's remote location and advanced instruments allow it to gather data that would be impossible to obtain through other means. This has enabled researchers to tackle fundamental questions about the universe's history and its future. However, the journey to these discoveries was not without challenges. The telescope's deployment required precise engineering to unfold its massive mirror and sunshield in the vacuum of space, a process that was meticulously planned and executed. The sunshield, a 5-layer structure designed to protect the telescope from the heat of the sun, had to be deployed perfectly to ensure the instrument's delicate instruments could operate at near absolute zero temperatures. Similarly, the telescope's instruments had to be calibrated to detect the faintest signals, a task that required years of preparation and testing. These challenges highlight the complexity of space-based observatories and the immense effort required to achieve scientific breakthroughs in such an extreme environment. As Webb continues its mission, the data it collects is already leading to new questions and hypotheses. For instance, the observation of massive galaxies in the early universe has sparked debates about the role of dark matter in galaxy formation, while the detection of unexpected chemical signatures in exoplanet atmospheres is prompting researchers to refine their models of planetary evolution. These findings are not just incremental advances, they are paradigm shifts that could redefine our understanding of the cosmos. The James Webb Space Telescope is not merely an instrument, it is a gateway to the past, a tool for probing the unknown, and a testament to human ingenuity in the pursuit of knowledge. With each new discovery, it brings us closer to answering some of the most profound questions about our place in the universe. The James Webb Space Telescope stands as a testament to human ingenuity, a machine built to peer into the cosmos and unravel the mysteries of the universe. But how did scientists arrive at the idea of such a telescope, and what steps led to its creation? The journey begins not with a single moment of inspiration, but with decades of planning, collaboration, and a shared vision to explore the unknown. In the 1990s, astronomers and engineers began to recognize the limitations of existing telescopes. The Hubble Space Telescope, launched in 1990, had revolutionized our understanding of the universe, but its capabilities were constrained by its design. To study the earliest galaxies, the formation of stars, and the atmospheres of exoplanets, a new telescope was needed, one that could capture light from the faintest and most distant objects. This vision gave rise to the James Webb Space Telescope, named after the former NASA administrator who championed the project. The telescope's mission was clear: to observe the universe in the infrared spectrum, a wavelength of light that can reveal the faint glow of ancient stars and galaxies. But achieving this goal required solving some of the most complex engineering challenges in space exploration. The first step was designing an instrument capable of detecting infrared light. Unlike visible light, which is emitted by hot objects, infrared light is emitted by cooler, dimmer sources such as the first stars to form in the universe or the atmospheres of distant planets. To capture this light, the telescope needed a mirror large enough to gather sufficient energy, but also one that could operate at extremely cold temperatures to avoid interference from its own heat. This led to the development of a segmented mirror system, composed of 18 hexagonal mirrors that could be folded for launch and then unfolded in space. The mirror's size was critical; it needed to be about 6 times larger than Hubble's to collect enough light from distant objects. However, the mirror's design also posed a challenge. It had to be lightweight enough to be launched into space, yet strong enough to maintain its shape under the stresses of deployment. Engineers solved this by using a material called beryllium, which is both light and durable. The mirror's surface was coated with a thin layer of gold to enhance its ability to reflect infrared light. Once the mirror was designed, the next challenge was creating a system to keep the telescope cool. Infrared light is easily absorbed by heat, so the telescope needed to be shielded from the warmth of the sun, earth, and moon. This led to the development of a 5-layer sunshield, a structure resembling a giant parasol. Each layer was made of a material that could reflect sunlight while allowing infrared light to pass through. The sunshield's design was a marvel of engineering, as it had to be both lightweight and highly effective at thermal regulation. The sunshield's deployment was another critical step in the telescope's journey. Once in space, the telescope had to unfold its mirror and sunshield in a precise sequence of steps, each requiring flawless execution. The complexity of this process was evident in the years of testing and simulations conducted on Earth. Engineers used mock-ups and computer models to ensure that every component would function correctly in the harsh environment of space. These tests were not just about verifying the design but also about preparing for the unknown, ensuring that the telescope could adapt to any unforeseen challenges. After years of development, the telescope was ready for launch. The James Webb Space Telescope was launched in December 2021 aboard an Ariane 5 rocket from the Guiana Space Center in French Guiana. The launch itself was a moment of immense anticipation, as the telescope had to reach a specific location in space known as the second Lagrange point, L2, a point where the gravitational pull of the Earth and the Sun balances, allowing the telescope to remain in a stable orbit. Reaching L2 required a precise trajectory, and the journey took several months. Once there, the telescope had to deploy its components, a process that took several weeks. The first major step was unfolding the mirror, a delicate operation that involved moving the 18 segments into their correct positions. Each segment had to be aligned with micrometer-level precision to ensure the mirror's shape was perfect. This process was followed by the deployment of the sunshield, which had to be carefully unfolded in tension to maintain its shape. Every step of the deployment was monitored closely, as any error could jeopardize the mission. The final phase of the telescope's commissioning involved calibrating its instruments and ensuring they were functioning as intended. This process took months, as scientists had to fine-tune the telescope's systems to account for any minor misalignments or thermal variations. The confirmation of the telescope's success came with the first images and data it transmitted back to Earth. These images, captured in the early months of 2022, revealed the telescope's ability to detect the faint light of distant galaxies, some of which existed just a few 100 million years after the Big Bang. The clarity and detail of these images were a testament to the telescope's capabilities, confirming that it had successfully overcome the challenges of its design and deployment. The confirmation process was not just about verifying the telescope's technical performance but also about validating its scientific potential. Scientists used the data to study the earliest galaxies, the formation of stars, and the atmospheres of exoplanets, all of which were previously beyond the reach of existing telescopes. The James Webb Space Telescope's journey from concept to confirmation was a remarkable achievement, a blend of scientific ambition and engineering precision. It required decades of planning, collaboration across international teams, and a willingness to tackle seemingly insurmountable challenges. The telescope's success is a reminder of humanity's capacity to explore the cosmos, driven by curiosity and the pursuit of knowledge. As the telescope continues its mission, it stands as a symbol of what can be achieved when vision, innovation, and determination come together to unlock the secrets of the universe. James Webb Space Telescope, JWST, definition and facts. This part of our deep dive into James Webb Space Telescope, JWST, definition and facts focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For centuries, humanity has gazed at the night sky, wondering about the vastness of the universe. But it wasn't until the 20th century that we began to unravel its secrets with the help of telescopes. The journey to understand the cosmos has been one of incremental breakthroughs, each new instrument pushing the boundaries of what we can see. Today, we're looking at one of the most ambitious projects in this long history, the James Webb Space Telescope. But to truly appreciate its significance, we need to step back and trace the path that led us here. How did we get from the earliest telescopes to a machine that can peer back 13.8 billion years? Let's explore the story of how our understanding of the universe evolved, the missions that came before JWST, and the scientific questions that made this telescope possible. The story begins in the 1960s, when scientists first realized that placing a telescope in space could eliminate the distorting effects of Earth's atmosphere. The first attempt was the Orbiting Astronomical Observatory, launched in 1966. Though it had some success, its short lifespan and limited capabilities showed that space-based astronomy was still in its infancy. It wasn't until the 1970s and 1980s that the concept of a dedicated space telescope gained serious traction. The Hubble Space Telescope, launched in 1990, became a landmark in this effort. For decades, Hubble revolutionized our view of the universe, capturing stunning images of distant galaxies, nebulae, and even the atmospheres of exoplanets. But despite its achievements, Hubble had its limits. Its instruments were optimized for visible and ultraviolet light, leaving infrared observations to other missions like the Spitzer Space Telescope, launched in 1998. While Spitzer provided valuable insights, its smaller size and shorter operational lifespan meant it couldn't explore the full potential of infrared astronomy. The limitations of these early telescopes highlighted a key challenge: the universe's most profound mysteries often lie in the infrared spectrum. Infrared light, which is invisible to the human eye, carries the signatures of the earliest stars, the formation of galaxies, and the atmospheres of distant planets. But detecting this light requires extremely cold detectors and large, sensitive instruments, something that Hubble and Spitzer couldn't fully achieve. Enter the James Webb Space Telescope. Conceived in the 1990s as a successor to Hubble, JWST was designed to address these gaps. Its primary goal was to study the early universe, observing the first galaxies that formed just a few 100 million years after the Big Bang. It also aimed to analyze the atmospheres of exoplanets, searching for signs of life, and to explore the formation of stars and planetary systems. These objectives were not just ambitious, they were essential for answering some of the biggest questions in science. How did the universe begin? What are the building blocks of life? And how do galaxies evolve over time? To achieve these goals, JWST required a radical leap in technology. The telescope's mirror, for instance, is 6 times larger than Hubble's, allowing it to gather more light and see fainter objects. But size alone wasn't enough. The telescope needed to operate in the infrared, which means it must be kept at an extremely cold temperature, just 40 Kelvin, or about -233 degrees Celsius. This required a revolutionary design, including a large sunshield that blocks heat from the sun, Earth, and Moon. The sunshield, a 5-layer structure made of a material called capton, is as thin as a human hair but capable of reflecting sunlight and radiating heat away. This engineering marvel ensures that JWST's sensitive instruments can detect the faintest infrared signals without being overwhelmed by thermal noise. The development of JWST was a collaborative effort spanning decades. NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA, worked together to overcome the technical challenges. One of the most complex aspects was the telescope's segmented mirror. Unlike Hubble's single, monolithic mirror, JWST's mirror is composed of 18 hexagonal segments, each coated with a gold film to enhance its reflectivity in the infrared. These segments must be precisely aligned and adjusted to form a single, perfectly shaped mirror. This required advanced robotics and a system of microsensors that can measure the position of each segment down to a fraction of a wavelength of light. The process of aligning the mirror took months after launch, a testament to the precision engineering involved. But the journey to JWST wasn't just about technology, it was also about the scientific questions that drove its creation. In the 1990s, astronomers began to realize that the universe was expanding at an accelerating rate, a discovery that led to the hypothesis of dark energy. This raised new questions about the nature of the cosmos and the forces that govern it. Meanwhile, the search for exoplanets was gaining momentum, with scientists detecting planets outside our solar system. These discoveries underscored the need for a telescope that could study the atmospheres of these distant worlds, looking for signs of water, methane, or other molecules that might indicate the presence of life. JWST was designed to do exactly that, using its high-resolution spectrographs to analyze the light from exoplanets and identify the chemical signatures of their atmospheres. The development of JWST also reflected the growing importance of international collaboration in space exploration. The project involved contributions from scientists and engineers around the world, with ESA and CSA playing key roles in the design and construction of the telescope. This global effort was a natural progression from earlier missions like Hubble, which also relied on international partnerships. However, JWST's scale and complexity made it one of the most expensive and technically challenging projects in space history. The budget for the telescope exceeded $10 billion, a figure that sparked debates about the cost of scientific exploration. Yet, for many scientists, the investment was justified by the potential discoveries. JWST was not just a tool for observation, it was a gateway to understanding the fundamental processes that shaped the universe. The launch of JWST in 2021 marked the culmination of decades of planning and innovation. But its story is part of a longer narrative, one that stretches back to the earliest attempts to peer beyond Earth's atmosphere. From the first space telescopes to Hubble's groundbreaking images, each mission built on the knowledge of the last. JWST represents the next step in this journey, combining the lessons of the past with cutting-edge technology to explore the cosmos in ways never before possible. As we look to the future, the discoveries made by JWST will undoubtedly shape the next chapter in our quest to understand the universe. And while the telescope's journey has only just begun, its legacy is already clear. It is a testament to human curiosity, ingenuity, and the unending desire to uncover the mysteries of the cosmos. The James Webb Space Telescope has already revolutionized our understanding of the cosmos, but even as it peers into the distant past, it has also uncovered profound mysteries that challenge our current scientific frameworks. While its instruments have provided unprecedented clarity on the early universe, the formation of the first stars, and the structure of distant galaxies, they have also raised new questions that scientists are still striving to answer. These unresolved issues are not just technical hurdles but fundamental puzzles about the nature of the universe itself. For example, the James Webb Telescope's ability to observe galaxies in the early universe has led to debates about whether these ancient systems formed in the ways we previously thought. Some astronomers argue that the galaxies observed by JWST may not be the first to form, but rather part of a different evolutionary pathway, one that could reshape our understanding of cosmic history. Similarly, the telescope's search for the first stars, known as population 3 stars, has revealed complexities that challenge existing models of star formation. These stars, which are theorized to have been the first to ignite in the universe, are incredibly faint and difficult to detect. The James Webb Telescope's instruments are designed to capture their faint light, but the data it has returned so far has sparked discussions about whether these stars behave as predicted or if there are alternative explanations for their observed properties. Another area of uncertainty lies in the James Webb Telescope's ability to probe the nature of dark matter. While dark matter remains one of the greatest mysteries in astrophysics, the telescope's observations of galaxy clusters and their gravitational effects may provide indirect clues about its distribution and behavior. However, the exact mechanisms by which dark matter interacts with visible matter are still debated, and the James Webb Telescope's data could either confirm or refute existing theories. Additionally, the telescope's instruments, such as the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, have pushed the boundaries of technology, but their performance in space has also revealed unexpected challenges. For instance, the James Webb Telescope's cryogenic cooling systems, which are essential for maintaining the sensitivity of its infrared instruments, have required careful calibration and maintenance. Any fluctuations in temperature or alignment could affect the accuracy of its observations, raising questions about the long-term reliability of its data. The telescope's role in studying exoplanet atmospheres has also introduced new uncertainties. While it has already detected the presence of certain gases in the atmospheres of distant worlds, the interpretation of these findings remains contentious. For example, the James Webb Telescope's ability to detect biosignatures, molecular indicators of life, has sparked debates about what constitutes a reliable signal. Some scientists argue that the data could be influenced by non-biological processes, while others believe the telescope's advanced instruments are capable of distinguishing between organic and inorganic sources. Moreover, the James Webb Telescope's mission has highlighted the limitations of our current models for predicting how light behaves in extreme cosmic environments. The telescope's ability to observe the universe in the infrared spectrum has allowed it to peer through cosmic dust clouds that obscure visible light, but this has also revealed complexities in how light interacts with interstellar material. These interactions may alter the way we interpret the data, forcing scientists to refine their models of light propagation and absorption. Another unresolved question involves the James Webb Telescope's capacity to study the formation of supermassive black holes in the early universe. These enigmatic objects, which are thought to have formed rapidly in the first billion years after the Big Bang, remain poorly understood. The telescope's observations of distant quasars and their host galaxies have provided new insights, but they have also raised questions about the timescales and mechanisms involved in their growth. For instance, some researchers are questioning whether the observed supermassive black holes formed through rapid accretion or if they were seeded by smaller black holes that merged over time. The James Webb Telescope's data may help clarify these debates, but the answers are far from certain. Additionally, the telescope's observations of galaxy clusters have sparked discussions about the role of dark energy in the universe's expansion. While dark energy is thought to be responsible for the accelerated expansion of the cosmos, the James Webb Telescope's measurements of galaxy distribution and motion could provide new constraints on its properties. However, the exact nature of dark energy remains one of the greatest mysteries in modern physics, and the telescope's data may either support existing theories or challenge them in unexpected ways. The James Webb Telescope's ability to study the atmospheres of exoplanets has also introduced questions about the potential for life beyond Earth. While the telescope has detected molecules like water and methane in the atmospheres of some exoplanets, the presence of these substances does not necessarily indicate the existence of life. Scientists are still debating what combinations of gases could be considered biosignatures and how to distinguish between biological and non-biological processes. For example, the James Webb Telescope's observations of exoplanet atmospheres may reveal complex chemical interactions that could be explained by both biological and geological activity, making it difficult to draw definitive conclusions. Furthermore, the telescope's observations of star-forming regions have revealed unexpected complexities in the process of stellar birth. While astronomers have long believed that stars form from collapsing clouds of gas and dust, the James Webb Telescope's high-resolution images have shown structures and dynamics that challenge existing models. For instance, the telescope's ability to resolve individual stars in distant star-forming regions has revealed that some stars may form in clusters or through interactions with neighboring stars, complicating our understanding of how stars evolve. These findings suggest that the process of star formation is more dynamic and varied than previously thought, but they also raise new questions about the conditions required for star formation in different environments. The James Webb Telescope's mission has also highlighted the importance of collaboration and interdisciplinary research in addressing these unresolved mysteries. The data it collects is being analyzed by scientists from diverse fields, including astrophysics, planetary science, and cosmology, each bringing their own perspectives and methodologies. This collaborative approach has led to new hypotheses and theories, but it has also revealed the need for more sophisticated models and instruments to fully interpret the data. For example, the James Webb Telescope's observations of the early universe have prompted discussions about the role of cosmic inflation in shaping the structure of the cosmos. While inflation is a widely accepted theory for explaining the universe's large-scale structure, the James Webb Telescope's data may provide new evidence that could either support or refine existing models. However, the exact mechanisms of cosmic inflation remain a topic of debate, and the telescope's findings may help bridge the gap between theoretical predictions and observational data. In addition to these scientific questions, the James Webb Telescope's mission has also raised philosophical and ethical considerations about the limits of human knowledge. As the telescope continues to gather data, it is becoming increasingly clear that many of the universe's mysteries are beyond our current understanding. This realization has sparked discussions about the nature of scientific inquiry and the role of technology in expanding our horizons. While the James Webb Telescope has already provided groundbreaking insights, its discoveries are likely to lead to even more questions, underscoring the fact that the pursuit of knowledge is an ongoing journey. The unresolved mysteries it has uncovered are not just technical challenges but fundamental puzzles that could redefine our understanding of the cosmos. As scientists continue to analyze the data from the James Webb Telescope, they are not only deepening their knowledge of the universe but also redefining the boundaries of what is possible in the quest for truth. These open questions and scientific debates are a testament to the complexity of the universe and the enduring curiosity that drives human exploration. The James Webb Telescope's mission is not just about answering existing questions but about discovering new ones, ensuring that the journey of discovery is as much about the unknown as it is about the known. As the James Webb Space Telescope continues its groundbreaking mission, the scientific community is already looking ahead to the next generation of space observatories and instruments that will build upon its discoveries. The JWST has already begun to reshape our understanding of the universe, from the earliest galaxies to the atmospheres of exoplanets. But its work is just the beginning. In the coming years, a series of ambitious missions and technological advancements will complement, extend, and even challenge the findings of the JWST, pushing the boundaries of what we know about the cosmos. These future projects are not just about gathering more data, they are about refining theories, uncovering new mysteries, and perhaps even revising the fundamental models that govern our understanding of the universe. One of the most anticipated follow-up missions is the Nancy Grace Roman Space Telescope, a NASA project set to launch in the mid-2020s. This telescope, named after the former NASA chief, is designed to conduct wide-field surveys of the universe, capturing vast swaths of sky in a single observation. While the JWST excels at deep, high-resolution imaging of distant objects, the Roman telescope will focus on mapping the distribution of dark energy and dark matter, two enigmatic forces that shape the universe's structure and expansion. By studying the subtle gravitational effects of dark matter on the distribution of galaxies, the Roman telescope will provide critical data to test theories about the universe's fate. Additionally, it will search for exoplanets using the microlensing technique, a method that can detect planets orbiting stars at great distances. This approach complements the JWST's work in exoplanet atmospheres, offering a new way to identify potential habitable worlds. Another key player in the future of space exploration is the Euclid mission, a collaborative effort between the European Space Agency, ESA, and the European Southern Observatory, ESO. Scheduled for launch in the early 2020s, Euclid will be positioned at the second Lagrange point, L2, the same location as the JWST, to conduct a comprehensive survey of the universe's large-scale structure. Its primary goal is to map the distribution of dark matter and dark energy by observing the distortions in the light of distant galaxies caused by gravitational lensing. These distortions, known as weak lensing, provide a direct way to measure the effects of dark matter on the cosmos. By combining Euclid's data with observations from the JWST, scientists will be able to create a more detailed picture of how dark matter influences galaxy formation and evolution. This synergy between missions will allow researchers to cross-check findings and refine models of cosmic expansion, potentially revealing new insights into the nature of dark energy. Meanwhile, the Plato, Planetary Transits and Oscillations of Stars, mission, also led by ESA, is poised to revolutionize the search for Earth-like planets. Scheduled for launch in the 2020s, Plato will focus on detecting exoplanets using the transit method, which involves measuring the dimming of a star's light as a planet passes in front of it. Unlike the JWST, which analyzes the atmospheres of exoplanets, Plato will prioritize identifying planets in the habitable zones of their stars, regions where liquid water could exist. By surveying a large number of stars over an extended period, Plato aims to discover thousands of exoplanets, many of which could be rocky worlds with conditions similar to Earth. These findings will not only expand our catalog of potentially habitable worlds but also provide targets for the JWST and future missions to study in greater detail. The combination of Plato's planet-finding capabilities with the JWST's atmospheric analysis could lead to the first definitive evidence of life-supporting environments beyond our solar system. Beyond dedicated missions, the JWST itself is expected to continue operating well beyond its initial 5-year mission. NASA has already extended its operations, and the telescope's instruments are designed for long-term use. As the JWST gathers more data, scientists will have the opportunity to refine their analyses and explore new questions. For example, the telescope's ability to peer into the early universe may reveal unexpected details about the formation of the first galaxies, potentially challenging existing theories about cosmic evolution. If the JWST detects anomalies in the light from these ancient objects, such as unexpected variations in their brightness or composition, future missions could be designed to investigate those phenomena further. The JWST's observations might also shed light on the role of dark matter in the early universe, a question that remains one of the greatest mysteries in astrophysics. In addition to these missions, the development of new instruments and technologies will play a crucial role in advancing our understanding of the universe. One such innovation is the potential for space-based interferometry, a technique that combines the signals from multiple telescopes to achieve unprecedented resolution. While the JWST operates as a single, massive telescope, future interferometers could link multiple observatories to create a virtual telescope with a much larger aperture. This approach could allow scientists to study the fine details of distant objects, such as the structure of young stars or the dynamics of galaxy clusters, with greater precision. Such advancements could complement the JWST's discoveries, offering a new perspective on the universe's most complex systems. Another area of potential breakthrough is the study of cosmic inflation, the rapid expansion of the universe in its earliest moments. The JWST's observations of the cosmic microwave background in distant galaxies may provide clues about the conditions of the early universe, but more detailed measurements will be needed to confirm or refine theories of inflation. Future missions, such as the proposed Large UV/Optical/IR Surveyor, LUVOIR, or the Habitable Worlds Observatory, HWO, could be designed to probe these questions directly. These missions, while still in the planning stages, represent the kind of ambitious projects that could emerge from the JWST's legacy. By building on the telescope's capabilities, they could address fundamental questions about the origins of the universe and the forces that shaped it. However, the future of space exploration is not without challenges. The JWST's discoveries may also lead to unexpected questions that require new approaches. For instance, if the telescope detects signs of life in the atmospheres of exoplanets, it could force scientists to reconsider the conditions necessary for life and the prevalence of habitable worlds. Similarly, if the JWST's observations of the early universe reveal anomalies that contradict current models, it could prompt a re-evaluation of the standard cosmological framework. These scenarios highlight the dynamic nature of scientific discovery. Each mission builds on the last, but also opens new avenues for inquiry. As these future missions and technologies take shape, they will not only expand our knowledge of the universe but also deepen our appreciation for its complexity. The JWST has already demonstrated that the cosmos is far more intricate and mysterious than we once believed. By continuing to explore the universe with ever more advanced tools, we may uncover answers to some of the most profound questions in science and perhaps even redefine our place in the cosmos. The journey of discovery is far from over, and the next chapter is already being written in the vast, uncharted expanse of space. The James Webb Space Telescope is more than just a tool for looking at stars, it's a time machine. By capturing light from the earliest galaxies, it allows us to peer back 13.8 billion years, to the moments after the Big Bang. This isn't just about seeing distant objects, it's about unraveling the origins of the universe itself. The telescope's ability to detect faint, redshifted light from those ancient galaxies is a triumph of engineering and science, offering clues about how the first stars and galaxies formed. But its significance goes beyond cosmic curiosity. The data it collects could reshape our understanding of dark matter, star formation, and even the potential for life elsewhere in the universe. Yet, the JWST's success isn't just about its advanced technology. It's a testament to global collaboration, with contributions from NASA, the European Space Agency, and the Canadian Space Agency. Every component, from the mirror to the sensors, represents decades of innovation and shared expertise. And while its primary mission is to study the cosmos, the telescope's legacy may also lie in inspiring future generations of scientists and engineers. As we continue to analyze its findings, one thing is clear: the JWST is not just expanding our view of the universe, it's redefining what we think is possible. If you've enjoyed this deep dive into the James Webb Space Telescope, consider subscribing to FactVerse for daily explorations of the cosmos and the science that shapes our understanding of it. Whether you're a seasoned stargazer or just curious about the universe, there's always more to discover. And if you have a question, a theory, or a guess about what the JWST might reveal next, drop a comment below. The universe is full of mysteries, and together, we're learning to unlock them.